Well, welcome to lesson 24. Julie, great lead-in to exponential functions. And yes, I decided to show up this one, our last video lesson. And yes, it's Peter, not Ernest Hemingway, so we're ready to go. From the previous examples, which was in lesson 23 that Julie just did, we can clearly verify that a linear function has a constant total change or rate of change. And that rate of change is equivalent to its slope. I hope you got that from the last lesson. An exponential function has a constant what? It has a constant percent change, which is the same as 1 plus r, which is the factor. 1 plus or minus r, actually. Which we also call the growth or decay rate. So there's the basics. Okay, so now we're going to look at three forms of exponential equations. They all have certain things in common. Obviously, they all have an output. But importantly, they have an initial value, a starting place. In the common form, it's A. In the continuous form, it's A. And in the standard financial example, it's P to the 0. So you start somewhere. And then you multiply it by a factor, a growth factor. Or it could be a decay factor. In the common form, that factor is B. In the continuous form, that factor is E to decay. And in the compound interest standard financial example, it's 1 plus R. And then it's raised to a certain amount of time periods or a certain amount of cycles, and that's the input X or T. So let me just give you one example of this. So let's rip our example right from the headlines. A certain state had 720 cases of COVID-19 on August 1st. If they are experiencing a 7% daily increase in cases, at this rate, how many cases will there be in 1 month? Now we're going to assume 1 month is 30 days because the rate that was given is a daily rate increase. So now we could do this. Well, first of all, the output is going to be the number of cases on that day in 1 month. That's just going to be the output. The input, what is the starting value? And good job if you answered 720. Now, what is the growth factor? And if you answered 1 plus R, which is 1 plus 7 over 100, which is 1.07, you would be correct. And I'll take another harder look at that. Now, I don't care about every day. I just want to know at the end of 30 days, how many cases will there be on day 30 if this scenario is happening? Now, we could use Excel. And we said this is 1.07. So we're going to start out with day 0, first day, initial value, 720 cases. And what we're going to do, I'm going to make that so what I'm going to do here is just take the 720 cases that we started with, our initial value, and increase it by 7%. And I would do that by going, I want 720 cases, multiply that by 1.07 and lock that. And I'm going to get 770 cases on day 1. And then on day 2 all the way to day 30. So I can just pull this down, day 1 all the way to day 30. And on day 30, I would have 5,481 cases. I'm just going to write that down there. 5,481 cases after 30 days using Excel. Taking the number and increasing by 7% each day from the previous day. That's number one. Look how much that goes. That's why it scares people. That's why they shut down places when they see this kind of a growth rate in many states. Okay, here's our two equations. Our first equation and our third equation from our book. Obviously, P here and Y here are just the outputs. So we can start out with the output equals. A is the initial value. P sub 0 is the initial value. So hopefully, right, the initial value is 720 times, and same thing here, 720 times 7%. That's the growth rate. How do you find the factor? In other words, how do you find the number that I'm going to multiply 720 by in order to increase 720 by 7%? And this goes back to this, right? 1 plus r. Actually, it has that 1 plus r right here. So we'll find out what 1 plus r is. It's going to be 1, and I'm increasing by 7%, which is 7 over 100. And I'm getting 1.07. So 1.07 is B, our growth factor. And it is also 1 plus r, because I just did it here. So it's 1.07. Now the last question is, what am I going to raise it to? What is this here and here? And the answer is great if you got it, 30 and 30. So these equations are extremely similar. They're just using different letters to represent things. And here they split 1 plus r apart. Here they're asking you to put it together before you put it in the equation. So let's do this. 720 times 1.07, and where's my raised to key? I don't see it. It's got to be here. I could go 1.07, 720 times 1.07 times 1.07, 30 times, but I'm getting all confused because I don't want to do it 30 times. I just want to use the raise to button. So I'm going to do it on my calculator out here, and I'm going to go 720 times 1.07 raised to the 30th power. I'm hitting enter, and I get 5481, which shouldn't be any surprise, which is exactly what I got with Excel, only here I did it in one step. Okay, I brought in Euler's number here, and the continuous form of the equation. There is the continuous form. And I want to explain what the difference is between the first equation and the third equation, which are really equivalent, and the middle equation, which is the equivalent, which is the continuous form of an exponential. And Excel always gives you this when you graph something. Okay, so I'm going to look at this here. Here's my file. And I'm just going to say that I have an initial balance of $100 right here. I'm going to put that in the bank, and I'm going to get interest every quarter. So remember this from chapter 1. The interest rate's 4%, but it's going to be 4 times a year. So it's going to be equals 4% divided by 4. And the periodic rate there would be 0.01, which as a percentage would be 1%. Whoops. Now, if I was going to compound it every month, right, then my periodic rate would be, if you recall, 4% divided by 12, because it's being compounded every month. And that, as a percentage, would be a little bit more, 0.333, right? So the percentage is less, but you're getting more compounds. So now I'm going to run these through. I'm going to put the ending balance at the end of 1 year up on our sheet. And the question I have for you as I make that transition, which one is going to, under which scenario will there be more money? Or will they be the same? And this actually goes back to that APY. But here we're compounding every quarter, and here we're compounding every month, right? Yes, I disappeared, but I'm still here. If you guessed that the monthly rate was going to give you a little bit more when you compounded it monthly, you would be correct. That's what I got when I ran it through the Excel file. Now what I'm going to do is the daily rate, and I'm going to do it with this formula right here. So my initial value is $100. And B, it's going to be, and you can 1 plus the periodic interest rate, which is 0.04 over 365. And I can either put that in my calculator, just leave it like that. I'll put all this in my calculator exactly as I'm putting here. Raised to the what power? And if you guessed 365, you would be correct. Now, I don't expect you to be able to repeat this, but if you're following the logic, that's good. So I'm going to put that in my calculator, and you should try it too. And I come up with 10408. So if I put $100 in at 4% interest, compounded daily, it's going to be a little bit more money than compounding monthly, which is a little bit more money than compounding quarterly, which would be a little bit more money than compounding semi-annually. Now, what if I wanted to do this? I wanted to compound it, and anybody know what that sign means? Infinite. If I wanted to compound it an infinite amount of times, well, it's going to be a little difficult to use this formula. I mean, what am I going to do? Y equals 100 times the factor, and the factor is 1 plus 0.04 over infinity raised to the infinite amount of times. Well, it's not going to work very well on your calculator. So from this idea, however, this is the equation that is derived. This is the continuous compounding formula. And it's also the formula used in Excel. So here we're going to use this equation to determine how much money you would have in a bank. If you put $100 in, how much you would have at the end of 1 year at 4% if you compound it continuously. Infinite amount, every millisecond. Okay? And it actually turns out it's not going to be much more than this. But this is how you would do it. So my output equals my initial value. That's A. Times E, which is Euler's number, which is E is approximately 2.7, blah, 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 blah. It is an irrational number, just like pi is an irrational number. But it's in your calculator as a little e. And that's raised to the rate, which is 0.04, or 4 over 100, times 1 year. So let's actually put that in the calculator. Now, all calculators are different, but let's just use this one. So we have 100 times E, which is the blue, that little E there. So you got to hit second E, raised to the 0.04, come down off there, times 1, which I really don't need to do that, do I? And I'm getting $104.08. So with our infinite compounding at 4% per 1 year, we got $104.081. So a little teeny bit more than daily compounding. Now, if you had bigger numbers and you did it for thousands of years for different items, it would make quite a big difference. But for this little example, it doesn't. However, the point is that this is continuous compounding. Okay, these equations, the following equations, these three, this one, and this one, are the same equation in the different forms that we've been using. First, you can see that the initial value is 100 in all three. And you can probably see, remember the first equation here and the third equation here, how similar they are. This just puts in 1 plus R, 1 plus the rate, while this one just adds them together. Now this one looks a little different, but I'm going to put in your calculator, you want to put it in mine, you put it in yours, E raised to the 0.3001, and see what you get. And you're going to get 1.35. which is pretty amazing. But this is continuous, so the continuous form, you don't need quite as much of a factor in order to accomplish what non-continuous is going to accomplish. So does this equation represent growth or decay? Growth or decay? And the answer is growth because it is greater than 1. And the rate is 35%. And the factor, that's the rate, right? And the factor is 1.35. What is the continuous rate for these examples? The continuous rate has to come from the continuous equation. And there is K, the rate. It equals K. And K, 0.3 is 3/10, which is 30%, or 30 over 100. What is the associated rate per unit? I kind of already gave it to you here, right? There's the rate. And you can easily get it from this form. And actually, you can easily get it from this form also. So if you had any kind of a rate, it's coming from 1 plus R, 1 plus or minus R, but it's basically 1 plus R equals 1.35. Subtract 1 from both sides, and you get R is 0.35, and 0.35 is 35%. Sometimes you can just really look at it, and sometimes you can go through this. Well, welcome to question 3. What you want to do in question 3 is, in the following examples, we're going to identify the starting value, the continuous rate, the growth or decay factor, that's going to be a factor, and the associated growth decay rate, and convert the given equation from Excel to the two other forms. So this is what the equation is given in Excel, right here, right? Hopefully you would know that that 1200 is the starting value. So it's the starting value for this equation. It's also got to be the starting value for these two equations here. So we could actually start those. Y equals, I'm doing AB to the X, 1200. So that's what we have so far. And for the last one here, we have P equals 1200. And then we'll have the rest coming. The continuous rate is the rate right here. That is K. That is 0.1655 over 1. So what is that over 100? You can do it that way, or you could just move the decimal 2 places, and you're going to get 16.55%. Now I'm going to change this. I want the factor here. This is just, it's a typo. These are all factors. So it's going to be like a factor, right? And you find the factor 1 plus R, right? So we need to find the factor. First we have to find what this growth rate is. And it's going to be just putting in your calculator e raised to the 0.1655 power. You just simply put that in your calculator and see what you get. And when I put that in and round it, I get 1.18. That is what you're going to multiply by. 1.18. That is 1 plus R. So what is the associated growth or decay rate? Well, this is 1 plus R. So it's 1 plus 0.18. 0.18, you hopefully would know that would be 18%. So now I have enough to do this because I have the growth or decay factor. So that's good for B. That's what B is, right? So it's times 1.18x. And this one here, it's 1 plus 18 over 100, or 0.18, however you want to write it, raised to, in this case, t. Okay, so B is U.S. population. And notice you want to change on your paper too. We're looking for the growth decay factor. Basically, that's the number that you multiply by 1 plus or minus r. Whatever that number is, that's the factor, right? So the starting value, of course, is right here, 0.0036. The continuous rate is right here. It's K. It's 0.0126, which is 0.0126 over 1, or 1.26 over 100, which is 1.26%. Okay, so I already have some stuff for our equations down here. I hope you can see. Now the factor is going to be what is 0.0036 being multiplied by? And it's being multiplied by E raised to the 0.0126. Now you want to try to put that on your calculator. And depending on how many decimal places you want, I'm getting 1.013. That rounded that. So that's what I am multiplying 0.0036 by. So that's the factor, 1.013. So the associated percentage rate would be, look, you can do it this way. This is 1 plus r here. So you can actually do this. You can go 1.013 equals 1 plus the rate. You can subtract 1 from both sides, and you can get the rate is 0.013. And 0.013 as a percentage is 1.3%. It makes sense because that's over 1, right? Okay, so now for this form, right, you have the output equals the starting value, which is 0.0036, times the factor. In this case, it's a growth factor because it's greater than 1. 1.013 raised to the x. And so in this form, we'll put the equation, right? Let's erase this here. Okay, that's cleaned up. So we're going to have our output, which is the population of the United States, equals the initial value, which is 0.0036, times 1 plus the rate, which is 1.3. That's the growth rate. 1.3 over 100 raised to the t power. Or you could make that 0.013 also. You could simply do this, 1 plus 0.013. Now look at this. This is an odd initial value. I suspect that X is actually the year, whatever the year is. So if you wanted to project the population for the year 2030, somewhere up here, you would use literally 2030 as X in this equation, 2030 as T in this equation, or 2030 as X in this equation. Well, let's take a look at what we have in this graph. Notice that this is actually an exponential decay. Notice all the other ones kind of went like this. Exponential growth. This is exponential decay. And you can see that by the value of K here. So this is decibels, which is a measurement of noise. And this is how many minutes is safe to listen at these decibel levels. So at decibel levels over 120, you don't want to listen very long, just maybe seconds. But when you get decibels at 90, you can listen for about 500 minutes. So that's what this is, safe listening times. So our starting value is 1e plus 0.8. That is the same thing as 1 times 10 raised to the 8th power, which is the same thing as 1 followed by 8 zeros. Which, voila, there it is, it's 100 million. The continuous rate is given by a continuous equation, which this is. And the continuous rate is 0.139, negative. 0.139 over 1 is the same thing as 13.9%. And this is decreasing. So the continuous rate is 13.9%, decreasing by 13.9%. Now the growth decay factor, notice this, we're going to find the factor. We're going to find this factor here. We already have the starting values. So this factor, we find it the same way we've been doing. E raised to the negative 0.139. Put that in your calculator, and we get 0.8702. That is our decay rate, decay factor, 0.8702. Now we want to find what is our growth or associated percentage rate. So we have the factor, and the factor is the 1 plus r. So 1 plus r equals 0.8702. I'm going to subtract 1 from both sides and put that in your calculator. And I'm getting negative 0.1298. And so that would be over 1. It's negative, so it's decreasing. move the decimal 2 places, I get 12.98%. So that would be my associated decay factor, this point rate, 12.98%. To accomplish this, I multiply by this, right? This is the factor. So now for the equations, let me erase this. And I have for the first one, my starting value for this equation. Same starting value, right? So I have my output equals 1 followed by 8 zeros. So I put those in. And now my growth, this is decay rate. It's time 0.8702 raised to the x power. And x in this case is your amount of decibels, right? For the second equation, there's my initial value. Then I have 1 minus 12.98 over 1. I'm sorry, 12.98 over 100 raised to the t. Now obviously, 1 minus 12.98 over 100 is 0.8702. So, okay, so this is a problem we just worked on, and here's a bonus idea for you. How would I get the output if given the input here? What would you use? What would you do? And how would you get it? Why don't you put it on pause and try to get the output for 92? And so there is my work, underlined in red, and that's how I got it. Now this will knock you out. This is going to be 278.5. What does it mean? Give me a sentence involving 92 and 278.5. And the answer would be at 98 decimals, or 92 decimals, it's 278.5 minutes that you can listen to this level of decimal noise output. That's the safe time for that level of noise. Okay, this is the last one of these problems. So you might want to try this. You might want to just pause it and try it on your own and then come back to it. But here we go. The starting value. What is the starting value? Well, that is right there. 20. So that already gives us information for A and information for P sub 0, as well as this formula, which is already given. The continuous rate has to come from the continuous function. This is the continuous function. There is the continuous rate. Negative 0.223. 0.223 over 1 is the same thing as 22.3%. And it's a decrease. So it's decreasing by 22.3%. Which is, in this actual problem, this is the days since there was a spill of contaminants, and this is the parts per billion that they're detecting in the water. So as the days go on, it's diluting the contaminants in the water, because this is an exponential decay. The growth or decay factor. Well, what is 20 being multiplied by? E raised to the negative 0.223. You got to be able to put that in your calculator. And I am getting 0.800, maybe I'll put the 1 in. So that is what you multiply the initial value by in order to get subsequent values. So the associated growth or decay rate, which I just should put a percentage here for this, coming off of that. Now, how did we get that? Well, 1 plus or minus r. In this case, it's going to be 1 minus r because it's a decay, it's less than 1, equals 0.8001. Subtract 1 from both sides, and I get a negative r equals whatever this is. And I'm getting 19.98. So that is the rate of decay. It's decaying by 19.98 or maybe even 99% per day, right? Per day. Actually, just to be technical about it, it looks like when I did it, it should be 19.99 or 20% really. Why don't we just make it 20%? So now I'm ready for converting to these forms. So for the y equals ab to the x, I have y equals the initial value of 20, the factor, which is 0.8001 raised to the x. And for the other equation, I'm going to get y equal, or I'm sorry, p equals, the initial value is 20. I'm going to get 1 plus 20 over 100. I'm sorry, 1 minus 20 over 100, which is essentially the same as this. This is just rounded. And that's going to be raised to the t power. So problem 4 is the last one I'm doing, and Julie's going to do a cameo for 5. The last problem, number 5. You will see her. Welcome, Julie. So carbon-14 is an element that naturally builds up in plants and animals during their life, and then will decay exponentially after death at a rate of 11.4% per millennium. That means per 1,000 years. So every 1,000 years, it decays by 11.4%. Using the equation 1 plus or minus r, determine the decay factor of carbon-14. Decay, right? 1 minus, and you could do it this way, 0.114 if you can, or otherwise put 11.4 over 100. And you get 0.886. So I'm going to take 100 and multiply it by 0.886. And then I'm going to get this value right here after 1 millennium, after 1 decay. And then I don't really, that's going to be 88.6. And then I'm going to take 88.6 and multiply it by 0.886. Put that in your calculator. I'm only going to round it to 1. So does that make sense? That would be the value in here. And I'm going to get 69.5. I don't know why it does that. Okay, so write down an equation of this form for the compound C14, which we just did. So how do we write down this equation? Well, the output, which is, where's my 69.5? My output, which is the amount of carbon, is going to be equal to my initial value, which is 100, right, at the beginning, decaying at a rate of 0.886. That's the factor, right, 0.886, raised to how many millenniums? So I could get this 69.5 by just using this equation and putting 3 in here. Remember, 3 means 3,000 years. All right, the graph on the right shows how Excel represents this equation. Here's the equation. That's how Excel does it. And an R squared equals 1 means it's a perfect fit. What is the continuous decay rate of carbon-14? Well, there it is. Negative 0.121. And the way you would get that is negative 12.1%, or a decrease by 12.1% continuously. Right? Continuously. That's the continuous form. Use the equation. Which form do you think is actually used? In this case, carbon actually is decaying all the time. Like this little carbon atoms just constantly decaying. So this one, in this case, makes a lot more sense. The reason this one's used in Excel is because it's very easy to use in higher level math. There's a lot of manipulations you can do with this that makes it very easy. All right, use the equation from Excel in your calculator to compute the amount of carbon-14 left after 8,250 years. So I should make you do that one and not even put the answer down. So we're going to use this equation, right? So you're going to put in your calculator 100 times E raised to the negative 0.121 times what? And if you answered 8.25, you would be correct. Because that's 8,000 times 1,000, 8,250 years. So I'll go to my calculator. You go to your calculator. I'll put the answer right there. And I'm getting, put it in red, or maybe I won't, 36.85. And it's going to mean grams. So, okay, Julie, take it over.
All right, thank you, Peter. Let's go ahead and take a look at what we have going on here. Chuck bought a tractor for $30,000 in May of 2000. The value of this tractor, even after the first few years, is shown in the table below. Let's go ahead and determine if the tractor is depreciating linearly or exponentially. All right, so in order to do this, we have to go back a little bit and think about what is the difference between a linear depreciation and an exponential depreciation. So if I go back a few pages, and I go back to this page where we discussed linear versus exponential. It's in the last lesson, the last page of the last lesson. Remember, if the total or absolute change is constant, so if the total or absolute change was the same, then we had what? A linear function. If the percent change was the same, as in this example below, then we have a what? Exponential function. So what we're going to do is we're going to create two extra columns here so that we can calculate the absolute change and the percent change. If the absolute change is the same, we're going to have what? A linear function. And if the percent change is the same, then we'll have an exponential function. Before we do this though, let's go ahead and change our data. Let's change it so it's just a little bit easier. We're going to change this $24,003. We're just going to change that to $24,000. So if your version of the workbook hasn't been updated yet, go ahead and change that to 24,000. It may already be updated. Now let's go ahead and really quickly calculate the absolute change. Remember, you're not going to use this first one. You're going to calculate the absolute change by this one minus this one. That's what's going to go in that first box. So we're going to go ahead and do 24,000 minus 30,000, which should be negative 6,000. Now I'm going to do 19,200 minus 24,000, and I should get negative 4,800. Well, we can already tell that these aren't the same, so it's probably not going to be linear. Let's see what our percent changes come up to be. If they're the same, then it'll be exponential. How do I calculate the percent change? I do the new minus the old, and I divide it by the old. So let's go ahead and take 24,000 minus 30,000, which we already have here is negative 6,000. So we're going to start with 6,000. Make it negative, and we're going to divide that change by what? By 30,000, the old value, and we're going to get negative 20%. Let's go ahead and calculate the next one. For the next one, we're going to take that 19,200, subtract the 24,000, which should give us what? That result already of negative 4,800. All right, then we're going to take that value divided by the old value, which is 24,000. And we get negative 0.2, which is negative 20%. Awesome. So we can see that the percent change, it seems to have a pattern that the percent change is going to be what? The same all the way down, which makes this function follow what? The exponential model. So is this tractor depreciating linearly or exponentially? Well, we decided it was exponentially. Why? Because the percent change column was the same. Does this data have a constant total change or a constant percent change? Well, remember, another way of saying absolute is saying total change. And another way of saying percent change is relative change. Don't let all the words confuse you. So does this data have a constant total change or a constant percent change? Well, it has a constant percent change, and that was what? Negative 20%. Let's go ahead and fill in the remaining values of the tractor in the chart to the left. I can use Excel if I want to expedite this, but this really isn't hard. How do I do this? I start with $30,000, and I'm going to multiply that by my what? My 1 plus or minus R value. My R is negative 20%. So if I want to multiply by 1 minus R, I'm going to multiply by what? By 1 minus 0.2, which is 0.8. So I'm going to take that 30,000, I'm going to multiply it by 0.8, and I should be left with this 24,000 right here. Oh my, there it is. I'm going to take that 24,000 and I'm going to multiply by 0.8, and I should be left with 19,200. Oh, this is cool. I'm going to multiply by 0.8, and I'm going to be left with 15,360. I'm going to multiply by 0.8. I'm going to be left with 12,288. Why don't you go ahead and finish that? And if you get tired like I am of putting it in the calculator and writing it down, it's okay. What we're going to do down here is you can see that we're going to create a scatter plot of this data in Excel. So save yourself some time and we'll just create a formula in Excel in a minute. Let's go ahead and do letter D first though. Write an appropriate equation that will accurately determine the value of the tractor after X years. Well, I have quite a few different forms of this equation. Let's go back and pull our forms of the equation from a few pages ago. I have the what? The common form, the continuous form, and then this other form. Let's go ahead and write those down. All right, so I have all three forms of the equation written. Now, all of these right here, my A, and my P sub 0, these are all my initial values. My initial value is my starting value. My starting value is all the way up here. It's what? At year 0, I bought that tractor for $30,000. So my starting value is $30,000. Now we'll just start with the common form, $30,000. Now I'm going to multiply that by what? By whatever my B value is. What's my B value in this equation? Remember, the B value, the e to the k power, and the 1 plus r value is all my growth or decay factor. So my growth or decay factor is going to be what? It's going to be that same thing that we multiplied by all these things to get the next number. It's that 1 plus or minus r value. So my growth or decay factor is going to be what? 0.8. I need to raise that to what? The x power. So now I have 30,000 times 0.8 to the x. Now what a lot of students want to do is they want to take 30,000 and multiply it by 0.8 to make it look a little bit nicer. But why can I not do that? Why? Because of PEMDAS. Remember, order of operations from back in the beginning of the semester. The first thing you handle is parentheses. The next thing you handle is exponents. After that, you can handle multiplication, division, and addition and subtraction. In this case, I have an exponent, so this piece is its own piece. So you have to do 0.8 to whatever that x value is going to be before you multiply by 30,000. Now remember what my x and my y values are. They're just what? Different points on the graph. For example, I've graphed this function for you. Let's take a look. So here's what the function looks like. It has a starting value of $30,000, and as the years go by on the x-axis, the value of the tractor goes down. All right. So I've made a table of values. Let's go ahead and get rid of me so that you can see this. I have a table of values here which matches the table of values that you should see on your paper. If I go ahead and put these points in, this first point is 0, 30,000. That means at 0 years, x is 0, my y value, my output, is going to be $30,000. If I go to 1 year, my input, x value of 1 year, is going to have an output of 24,000. I can continue through all of these values, and the x just represents a different year on the graph. So at 4 years, my tractor is going to be worth $12,000. I could extrapolate my data and look all the way up at 20 years, and in 20 years, my tractor is only going to be worth, $345. The input is the years, the output is the value of the tractor. So hopefully this makes a little bit of sense as to why we have an x value and why we have a y value. They just represent different years and different tractor values. All right, so in this equation we put 0.8 because 0.8 was what? Our growth or decay factor. And all that B stands for is what? Your growth and your decay factor. Now, let's see if we can come up with one of these other two equations. Y equals A times e to the kx. Well, e to the k is our growth factor. It's not just the k value. You have to do e to the k. So we need something that says e to the k equals 0.8. This is a bit challenging for us to solve in this class because we haven't discovered logarithms yet. If you've taken pre-calculus, you can solve this by the rule of logarithms or by taking the natural log of both sides. However, in this class, we're going to settle for Microsoft Excel to give us this equation. Before we go to Excel though, let's try and create this third equation here, this one on the far right. My initial starting value is $30,000, and I'm going to multiply that by what? 1 plus r, or 1 minus r. In this case, we had what? A percent change of negative 20%. We said our decay factor was 0.8 because we took 1 and subtracted our rate of 20%. So really all this is it's 1 minus 0.2 to the t value, and t is going to represent time, and my y, or my p in this case, is going to represent the tractor value. So you should be able to come up with these equations giving a set of data. This one you should be able to get using Excel. So let's go ahead and create that in Excel. So what I want you to do in Excel is just input this top stuff, and then we'll go ahead and we'll create the rest of this really quickly together. So go ahead and open your Excel file. And let's go ahead and enter our data. All right, now that we have our data in here, is what we want to do is we want to make sure that we do what? We drag this down so I don't have to copy it all the way down, so I don't have to type all the way down to 10. So go ahead and put those things in so we can get down to 10. I'm going to put in a formula because I'm lazy and I don't want to type those numbers in, and I don't want to calculate 8, 9, and 10 on my calculator. So how did we do this? We took this value and we multiplied it by what? 0.8. So 0.8 times the previous value. I can go ahead and I can copy this down, and I'm going to get my numbers instantaneously, and look how nicely they match. Okay. Now that I have my data in here, I want to create a scatter plot of the data. Easy. Go ahead and highlight your information. Go to insert, and you're going to insert what? A scatter plot. All right, so I have my scatter plot with my value of my tractor. Now that I have my scatter plot, it's telling me to what? Include both a linear regression line and an exponential regression line on the same graph, and state the R² values for each. All right, let's see if we can do that. So if I want to add a linear regression model, I'm going to do a trend line, add it in there. I'm going to do what? Go all the way down to the bottom, and I'm going to display the equation and the R value. All right, so I have, this is my linear one. I'll make it bigger so that everybody at home can see it. That was my linear equation. Now, let's see if we can add another equation onto this. I'm going to click on the plus sign again, and this time I'm going to click on trend line, and I'm going to add exponential. You see how I added 2 in there? Sometimes it's a little bit difficult to do, but if you play around with it a little bit, I'm sure you'll get it. So what I want to do is I want to add this. I have the trend line in there. Let's go ahead and add the equation of the R². We have exponential, more options. We want to make sure it's clicked exponential here. We want to go down and we want to include the equation and the R value. There it is. Once I have that, I'm going to make it bigger for you so everybody can see. And I'll turn it into red so that we can differentiate between the linear and the exponential. Now, look how cool this is. We have what? We have my exponential model giving me an R² value of 1, and my linear model is giving me an R² value of 0.91. Which one do you think is going to fit that data better, and why? Well, I'm going to say that the exponential fits the line better. Why? Because it has a what? An R² value of 1. Now, the next question, what is the decay factor and the decay rate from the equation in Excel? Does this match what we found in part B above? Let's go ahead and grab that equation from Excel. It's y equals 30,000, which is my initial value, e to the negative 0.223x. Don't forget, once you're done with the lesson, you're going to want to submit this Excel file to Canvas. Now, from this, we want to go ahead and get a decay factor and the decay rate. Well, the decay factor is just the what? The 1 plus or minus r. We know my decay factor is 0.8. How do we get the decay factor from this equation? It's going to end up being what? E to the negative 0.223x is the same as my decay factor, which is e to the x, which is same as my decay factor, which is 1 plus or minus r, which is the same as my decay factor, which is the b. So let's go ahead to our calculator and see if we can calculate negative e to the negative 0.223. And I'm going to go ahead and grab my cell phone calculator because I'm sure that's what most of you guys are working with. So we want to put in e to the negative 0.223. My e button is down here. I have 2 of them, right? I'm going to use this one here just because it's a little bit easier. E gives me that, and then to raise it to the negative 0.223, I want to use that x to the y key. X to the y of 0.223. And I want it negative, so I can put the negative in. And when I press enter, what do you think we're going to get? I think we're going to get something that looks like 0.8. Why? Because our decay factor is what? 0.8 from right here. That's what our B value was. So we got that e to the negative 0.223 is about 0.8. That's our decay factor. Remember, factor just means multiply. It's the 1 plus or minus r that you're multiplying everything by. Awesome. Now the growth or decay rate is what? It's going to be that 20% that our tractor is depreciating by. Well, what does this mean? Well, a decay factor of 0.8 means that a tractor decays by 20% yearly. Does this match what we found in Part B above? Well, Part B gave us what? A constant percent change of negative 20%. And in Part D, we had a decay factor of 0.8, or what? A decay factor of 1 minus 0.2. So yes, everything matches from Parts B and D from what we calculated above. Now I have a bonus question for you. What is that tractor worth in the year 2019? He bought this tractor back when? In 2000. So what's that tractor worth 19 years later? What are you going to do? Well, I'm going to take 19 years later and I'm going to plug it into the equation. 30,000 times e to the negative 0.223 times 19. And this is going to be what? This is going to be extrapolation. Why? Because we're extrapolating what would happen in the future. It's not within that same domain or range that we started with. So we're extrapolating out 19 years. Let's go ahead and calculate that on our calculator. Order of operations tells me I want to start with what? The exponents first. So I'm going to start with 0.223. I'm going to make it negative. I'm going to multiply by 19. I'm going to get negative 4.237. I'm going to go ahead and I'm going to type $30,000 times e to the exponent of 4.237 negative. And I should be getting $433.53. So my tractor that's 19 years old is only going to be worth $433.53. Is 433 a good estimate? Well, let's go ahead and look at our graph. Remember, at 20 years, we said that what? 345 is a good estimate. All right, but does that necessarily follow the same model as you extrapolate that many years out? You have to think about what happens with the value of old items. Some of them become obsolete because none of the parts work anymore, and other ones become antique and they don't follow the model that you would expect them to follow. Remember the danger of extrapolation. We will eventually run into effects outside of our normal model's range that aren't going to make sense. Does 19 years, is that out too far outside of our model's range so that it doesn't make any sense? That's up to you to decide. So this concludes lesson 24 on exponential equations. I hope you guys enjoyed it. Great job, and good luck on the homework.